Hello and welcome to this week's lesson on sequences. Today we're going to learn how to identify the difference between an arithmetic and geometric sequence, write a function rule for a given sequence. Take a look at these pictures. Can you find a number pattern in these pictures? Take a moment to think about it. Notice we see this spiral in these different rectangles and all these different geometric patterns within these objects in nature. They follow a pattern. Look at the box below. This box is of area 1, this box is of area 1, this box is of area 2, this one is 3, this one 5, this one 8, and the pattern that it's describing is called the Fibonacci sequence. It's repeated over and over again in nature. So number patterns just don't happen in math, where we use them all the time. They happen in real life, out in nature themselves. So what is a sequence? Well, a sequence is an ordered list of numbers that follow some pattern. So for example, 1, 5, 9, 13, 17. If I'm looking at this list of numbers, it looks like we just start with 1 and then we keep adding 4. Here's another example. 3, 6, 12, 24, 48. In this case, it looks like we start with 3 and then we just keep multiplying by 2. So 3 times 2 is 6, 6 times 2 is 12, and so on. Here's another example. This one's a little bit harder. But in this case, it looks like we start with 2, and then to get from one number to the next number, we multiply by 2 and then add 1. So for example, 2 times 2 is 4, plus 1 is 5. 5 times 2 is 10, plus 1 is 11. 11 times 2 is 22, plus 1 is 23, and so on. The dot, dot, dot afterwards mean that this pattern keeps going forever and ever, and I could write out as many numbers in this list as I wanted. Alright, so a sequence can also be represented by a table, as you've seen in your lessons. So let's take the example that we had earlier, 1, 5, 9, 13, and 17. We can write it in a table in this way, right, where I have in 1, 2, 3, 4, 5. You've seen that in your lesson. In our output, the sequence itself generated as a table of y values. So each number in this list is called a term. All right, and the first number in the list is called the first term because it's the first number in the list. So the second number in the list is called the second term, and so on and so on. In this case, the fifth number in this term is 17. We refer to that 17 as the fifth term because it's the fifth number in the list. So this n that you're seeing in the table is just the value, is the place value that it is in the list. So this is the first term, the second term, the third term, the fourth term, and so forth. And that's all that n represents. So it's always 1, 2, 3, 4, 5, going on forever and ever. All right, so we have two types of sequences that we're going to talk about today. The first one is called an arithmetic sequence. Right? So an arithmetic sequence, again, is an ordered list of numbers where we add or subtract the same number each time to get from one term to another. And that number that we're adding or subtracting each time is called the common difference. The other type of sequence we're going to talk about is called the geometric sequence. Right? And a geometric sequence is a list of numbers where we multiply or divide by the same number each time to get from one term to the next. And the number that we multiply or divide by each time is called the common ratio. So let's talk about the first type of problems that they have in your lesson. Right? It's called identifying the type of sequence and finding the next term. So they might give you a table like this, and they say determine whether the sequence appears to be arithmetic or geometric, then find the next term. In this case, the next term is the fifth term. All right, so I'm looking at this list, and I'm looking at the output y's. All right, and we got to decide the very first thing that I always try to do when I'm looking at an ordered list of numbers to see if it's arithmetic, meaning see if I can add or subtract the same number each time to get from one term to the next. So to get from 11 to 7, I could subtract 4. And I'm going to try that again and see if it works for the next term. Well, 7 minus 4 does give me 3. And 3 minus 4 does give me negative 1. So this sequence has a common difference then of negative 4. And because it has a common difference, that makes it an arithmetic sequence. Now let's find the next term. Okay, so to find the fifth term, we should take the fourth term, right, the last term we just had, and subtract 4 because that was the pattern that we found. So that means I should take negative 1 and subtract 4, and then we get negative 5. So the next term, or the fifth term in this case, is negative 5. Let's try another one. So determine whether this sequence appears to be arithmetic or geometric, then find the next term. Remember, so I am looking at the y. I'm looking at the output here, the y values, because those are the actual numbers in the sequence. So I'm going to write those out. And the first thing I try to do, again, is I try to see if it's arithmetic, meaning I can add or subtract the same thing to get from one number to the next. Well, if I take negative 2 and I subtract 6, that can give me negative 8. But then if I take negative 8 and subtract 6 from that, I don't get negative 32. I would get negative 14. So now I know that it's not arithmetic. I can't just add or subtract the same number to get from one term to the next. So then the next thing I try to see if I can multiply or divide by the same number to get from one term to the next. So in this case, it looks like I could take negative 2, and multiply it by 4 to get negative 8. Then I could multiply negative 8 by 4, and it does give me negative 32. And negative 32 times 4 is negative 128. So since this sequence has a common ratio of 4, remember that's what the number we're multiplying each time to get from one term to the next, then that tells us that this sequence is geometric. To get to the next term, then we should take the last term, which is our fourth term in this case, and then multiply it by 4. That means take a negative 128 and multiply it by 4. So in this case, when we take negative 128 and we multiply it by 4, we get 512. So in this case, negative 128 times 4 is negative 512. So you decide, take a turn here and practice this sequence. Decide whether this sequence is arithmetic or geometric, then find the next term. Take a moment to pause the video and see if you can determine 1, what type of sequence this is, and then 2, what the next term is, in this case the fifth term. Alright, so you should have tried adding or subtracting first to get from one term to the next to see if it was arithmetic. And if you did so, you would have seen that you could subtract 5 from each term to get from one to the other. That means that it was arithmetic. Now we need to find the next number in the list. Well, the next term you should have gotten is negative 19, because negative 14 minus 5 is negative 19. Let's practice another one. Take a moment to pause the video and determine whether this sequence appears to be arithmetic or geometric. Then find the next term. Alright, so the first thing I would have tried to see if it was an arithmetic sequence, if I could add or subtract the same thing to get from one number to the next. So I could take 3 and add 6 to get to 9. Then if I took 9 and added 6, I don't get 27. I would get 15. So that tells me that it's not arithmetic, because I can't just add the same number to get from one term to the next. So then I tried to see if it's geometric. So I asked myself, what can I multiply 3 by to get to 9? Well, I could multiply it by 3, because 3 times 3 is 9. Let's see if that continues. 9 times 3 does give me 27. 27 times 3 does give me 81. So this sequence is geometric. The next term would have been 243, because 81 times 3 is 243. The next thing we want to learn how to do is to write a function that describes a sequence, right? And that can be a little harder depending on how complicated the sequence is, what the rule is, what the pattern is. But here are some basic steps for writing a function for a sequence. One, you should create a function table. Next, determine the rules that generate the sequence. That means you need to figure out what we can do to the n to get to the y. So what we can do to the term number to get to our number in the sequence, the actual value of it. And then we can check that our rule works for each term. So let's take the sequence, 3, 4, 5, 6. First thing I'm going to do is write a table. So remember in my first table, my n values, those are just the term numbers. So I'm going to write out, I have 4 terms listed here, but remember this sequence does go on forever. But I'm just going to write out the first 4 terms. So I write n as 1, 2, 3, and 4. And then I put the values, the actual values of the numbers in the sequence underneath their appropriate terms. So we have, here you can see we have 3 is the first term, 4 is the second term, 5 is the third term, and 6 is the fourth term. Now the next thing we have to do is ask ourselves, what can I do to the n this time to get to y? So I'm not asking what I do to get from one y value to the next. Because we can see between this pattern 3, 4, 5, 6 that we're just adding 1 each time. But I'm not asking you what you have to do to get from one y value to the next. I'm asking you to try to figure out what you can do to this n value to generate the y value. So what can I do to 1 to get to 3? And whatever we try to come up with, it has to work for every single term in the sequence. It has to work for all the numbers to generate that list. All right, so maybe I'm going to guess and check. So I ask myself, I'm looking at the first term, this 1 and a 3, and maybe I decide that, well, I could take 1 and multiply it by 3 to get to 3. And we can see that that does work for the first term, but it doesn't work for the second term because 2 times 3 is 6, not 4. All right, so that didn't work. So now maybe I'm going to guess that I could add. So if I took the value in the first term, the term value of 1, and added 2, I do get 3. Now let's check to see if it works for the second term. If I take 2 and add 2, we get 4. If I take 3 and add 2, we get 5. If I take 4 and add 2, we get 6. So you'll see in your lesson that they often write a table like this, where they'll list out the n values, the rule, and then the output, the y that we get. So in this case, we can say the rule is taking the n value and adding 2. So notice here where I've written the rule 1, 2, 3, these numbers in black are just the term number, the n value. And what's in red here is the plus 2 is what I did to that n to get the y, because notice that 1 plus 2 here is 3, and 2 plus 2 is 4, and so on. So then if I took any n value, any term here, n, that's where this n comes from, and added 2, I would get whatever the y value is. So now I could write the function rule that y is equal to n plus 2. So remember what n is. N is the term values up here. So that means if I wanted to get the 10th term, I would just plug in a 10 where the n is and add 2. So let's try this one. Let's write a function to describe this sequence. 2, 4, 6, 8. All right, well, let's write a table. All right, so I list a table, and across the top, remember, I'm just listing numbers 1, 2, 3, the whole numbers in order. Those are the term numbers. And the y, the output, is the actual numbers in the sequence. Now remember, the next thing I'm trying to do is ask myself what I can do to n to get to the y. Because it's pretty easy to see that we're just adding 2 each time when I look at the list, but that's not what I'm asking you. Don't get confused and think that maybe this means that it should be y equals n plus 2. Because notice if I say y equals n plus 2, then that means I could take this 3 and add 2 to it and get my y value. But 3 plus 2 is 5, not 6. Right, so think about what do I have to do to this number up here in the top? What do I have to do to get to the bottom number? What can I do to it? And it has to work for all the numbers. So I kind of look at the first number in my list and I guess, remember, I'm trying to see if I can add something to it first. Then I'll see if I can multiply by something. Then I'll check the other numbers to see if it works for all the other numbers. If neither of those two things worked, then I would be looking for a combination. I'd be looking for maybe there's something I can multiply by and then add or subtract. In this case, I'm going to guess first that maybe we add 1, right? Because look, 1 plus 1 would give me 2 in the first term. So then I have to check the second one, and I see that 2 plus 1 is 3, not 4. So I know it's not just adding 1 to n. So that didn't work. So now maybe I guess that we multiply it by 2, because 1 times 2 would give me the 2. So I'm going to keep checking to see if that works for the rest of them. Well, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, so that works for each term. So now I'm pretty confident that the rule is take the n value, whatever it is, and multiply it by 2, and that will generate our sequence, our output of y values. So finally we can say the y value is equal to 2 times the n value. Let's write a function that describes this sequence, and this looks more like the type of problems that you get on your checkpoint. So in this case, they give us a sequence, then they want us to match up that sequence to the correct function rule. Well, they tell you that maybe here's a hint, you should start by writing the table, the function table. Okay, so here's our function table with our n values, and our output is the sequence itself. So remember, now we're trying to figure out what we can do to n to get to the y. Since we have our answers listed here, A, B, C, D, it's one of these numbers, let's work backwards this time from the answers using substitution. So what do I mean by that? I mean, let's take A here, and if the answer is A, then when I plug in each of these n values, I should get the output, I should get the y value that's listed in this table. So I'm going to plug in the first number. I'm going to plug in 1 for n in A and work it out and see if I get the y value that's listed here. So in this case, if I replace n with 1, because I'm just checking to see if I plug in a 1, will I get a negative 1 for y? I would get 2 times 1 minus 2, and 2 times 1 is 2, minus 2 is 0. But in this case, the y value should be negative 1, not 0 when I plugged in a 1 for the n. So then I know that A is no good, so that's a no. I'm going to check to see if B is correct, if y is equal to the n value divided by 2. Well, if I plug in the very first term, and I take 1 and I divide it by 2, I get a half, or 0.5. And according to the table, I should get negative 1, so I know that cannot be correct. And then I'm going to check to see if C is correct. So I'm going to replace the n with the very first term number, which is 1. Then I would just get that y is equal to 1 when the n is 1. But we see that when n is 1, y should be negative 1, so I know that this is also incorrect. So that does mean that D has to be correct in this case, but let's just check to see. If I replace a 1 where the n is in this equation, I get 1 minus 2, which is negative 1. And that is the value that we wanted. Just because the first one works, though, doesn't mean that it's the answer. We have to check at least a few of the others. So let's check the second term. Well, if I replace n with 2, then I should get 2 minus 2, which is 0, which is the output we were looking for when I plugged in a 2 for the n. So now I know that answer D is correct. I could check the other ones, but since it is our last choice in this case, and it worked for the first two, I'm going to assume that it's going to work for the other two, or any numbers that I want. How about we write a function to describe this sequence? So here they're telling us that Kat made 4 paper cranes on Monday, then 6 cranes on Tuesday, then 8 cranes on Wednesday, and write a function that describes this sequence. And then they give you the answer choices here. So I'm going to take a moment, I'm going to go ahead and I'm going to write my function table. I want you to take a moment to practice to see if you can decide which of these function rules describes this sequence. Alright, so you had 2 ways to do it. You could have gone about writing your own function rule given the n values and decide what you have to do to n to get to the y. Or you could start plugging in the n values in each of these equations and checking to see that you get the correct outputs. So in this case, I would have also gone and done working backwards from the answers to see if I could generate the sequence by plugging in the n values, because this pattern is a little bit more complicated than just multiplying or adding. So in this case, if I plug in a 1 in this option A, I would get 2 times 1 is 2. So when I plugged in a 1 for n, I get an answer of 2, but I should have got 4. So now I know that option A is incorrect. I'm going to try B. So I'm going to go ahead and replace the n with 1. And go 1 times plus 2. That gives me 3, but again I should have gotten 4. So now I know that B is incorrect. When I try option C, if I replace n with 1, I would get 2 times 1 and then add 2. So 2 times 1 plus 2 does equal 4. All right, so that worked for the first one. Well, let me check the second term. So when I plug in a 2 for the n, I would get 2 times 2 plus 2, which is 4 plus 2, which is 6. So it worked for the second term. Let's go ahead and check the third term since there's only 3 terms here. 2 times 3 is 6, plus 2 is 8, and we were looking for it to generate an 8. So now I know that this is the correct answer, that C is the correct answer. Now at the end of this video, I'm going to give you guys a summary video, and then after that I want you to make sure that you go back to your course announcements, and under the Asynchronous Session 5, make sure you click on and answer the questions and submit the form.
In this lesson, let's learn how to identify patterns in a sequence. And we need to tell whether each sequence of y values is arithmetic, geometric, or of any type of sequence, right? And we need to also find y when the n is 4. What is a sequence? A sequence is an ordered list of numbers, right? A sequence is nothing but an ordered list. And when I look at a sequence here, n is the position in the sequence, right? The first term, the second term, the third term, and the fourth term. And y is the value of each term. A sequence is made up of terms. Okay? When n equals 1 means the first term. When n equals second means the second term, etc. Now there are many different types of sequences. It's called an arithmetic sequence. Okay? If the second term value is the first term value plus something. So when I add some number, add the same number, right, to the previous term to get the new term, that's called an arithmetic sequence. In a geometric sequence, we multiply, right, the previous number with the same value. Multiply previous term with some number to get the next one. And remember that some number remains the same. It's the same number every time. Let's learn using the examples given to us on the left. In this case, what do I see? N equals 1, which means the first term is 16. Okay, that's good. Second term is 13. So if it was an arithmetic sequence, what did I add to 16 to get to 13? What did I add to 16 to get 13? Well, if I add negative 3, right, I will get 16 when added to negative 3 will give me 13. So this number that we were looking for, right, that moves the sequence from one term to the next could be negative 3. Let's see if that's true. Third one, the value is 10. So if I take 13 and I add to 13 negative 3, do I get 10? 13 minus 3 is 10. So as we can see, this sequence moves from first term to the second term to the third term by the addition of the value negative 3, which means this is indeed an arithmetic sequence. Okay? Now let's try the second one. The second one says that the first term is 3. Second term is 9. So what have I done to 3 to get to 9? I have added 6 to get to 9. So this could be an arithmetic sequence where I add 6. Now let's take the next term. From 9, I should have added 6 to get to the next term, which would have given us 15. But that is not true because the next term is 27. So we know this is not an arithmetic sequence. Let's try a geometric sequence. So the first term is 3. And the next term is 9. What can I multiply 3 by to get 9? Well, 3 times 3 is 9, right? So if this is a geometric sequence, then the value that I'm multiplying by is 3. Okay, let's try some more. Now, if I take the previous term, which is 9, multiply by 3 again, do I get the next term? 9 times 3 is 27. Yep. So as we can see, this is a geometric sequence. because to get from one term to the next, I multiply by the same number, which is 3. Now, let's do this. Let's compute the fourth value. When n equals 4, or the fourth term, here we went from 13 to 10. So the next one would be 10 plus minus 3, which would 10 subtracted 3, take away 3 from 10, which gives me 7. Okay. Here it would be 27 times 3, which would be 81. Okay. You see how I'm doing this, right? This is the arithmetic sequence. This is the geometric sequence. Now let's try the third problem, which says when n equals 1, the first term is 2, right? Second term is, first term is 4. Second term is 9. So I could have added 5 to get to 9. Now this next term is, I start with 9, I add 5. Do I get, the answer is 14. But I'm supposed to get 16. This doesn't work. So it's not an arithmetic sequence. Let's see if it's a geometric sequence. Let's take the first term, which is 4, multiply it by something to get 9. Okay, what do I have to multiply by to get 9, right? I have to multiply by 9 over 4. Okay, so let's assume this is the number. Then I take 9, multiply by 9 over 4. What do I get? 81 over 4. Is that the next number? That's 16, not equal. So this is not a geometric sequence either. So the answer to this is other type of sequence. But let's figure out what type it is. What do I see? The first term is 2 squared, which is 4, right? Which is taking the next term, the value of the next term, and putting the square of it. So the next one, second term is, so if the first term is 2 squared equals 4, second term is 3 squared equals 9, right? You can see that. The third term is 4 squared, 2, 3, 4. 4 squared equals 16. That's correct as well. So the fourth term would be 5 squared, which is equal to 25. What's the function here? The function is y equals n plus 1 squared. So to compute any value of y, we take the value of n, which in this case is 4, add 1 to it, gives me 5, squared is 25. Okay? So in order to look at arithmetic, geometric, or other sequences, we need to figure out if the previous term, to get to the next term, are we adding a number or are we multiplying a number? If we're adding, it's arithmetic. If we're multiplying, it's geometric.